Okay, as usual, we're giving it a little bit of time for folks to join us. All right, we've probably got whoever's going to join us. I think we're just one person in the audience tonight. All right, um, so maybe we'll get some more, maybe not. All right, so last time we were talking a little bit about the Cauchy-Riemann equations. We're going through holomorphy, talking about complex differentiability, analyticity, as we're calling it here, or holomorphy. We're using it interchangeably. Um, and we're talking about the big kahuna, the Cauchy-Riemann theorem. This theorem gives us the real meat of what makes a lot of complex analysis work behind the scenes. This is the little trick that we will just keep using. It's the result that just keeps giving. So we're going to give some attention to it, and we're actually going to go through and prove it. It'll be not too bad. However, while we were talking about some of the implications of the so-called Cauchy-Riemann equations last time, I noticed that right at the end of class, I made a grievous sign error that I am mortally embarrassed of. I've left it up on the screen right here. Namely, when I wrote the determinant, I put a plus between the two terms. We should all know that the determinant of a 2 by 2 matrix is equal to AD minus BC. I accidentally put plus right here, so I need to correct my awful mistake and be very clear that the thing I should have written was a minus right there, which would then, of course, when I go through and I put the minus, or when I take the partial u partial y and sub it out for a partial v partial x, a minus partial v partial x, that would then become a plus. So that's what I was trying to point out. I think I said a difference of squares, and I immediately knew something was wrong. A sum of squares. In fact, if you'll notice, and we'll find out very shortly, this is going to turn out to be a modulus. So the determinant of the matrix of partial derivatives will be the modulus. It's actually a kind of cool little trick. So we'll look at that in a little bit. But these Cauchy-Riemann equations, let's state the entire Cauchy-Riemann theorem in its full bloody glory that you see it in the textbook. And I'll make this series of layers a little bit smaller so we don't take up quite as much room. All right, so let's zoom in a bit, make it a little easier for everyone to see. All right, so the Cauchy-Riemann theorem, in its full glory, begins with A, an open set in C, and a function f from A to C. Then f prime of z naught exists if and only if f is differentiable in the sense of real variables at z naught, which is x naught, y naught, and the functions u and v, where we're writing here, f of, think of it like this, f of x, y, right? F of z being f of x plus iy, where, z is x plus iy. We're writing this as uxy, oops, made a mistake writing that y, plus vxy times I, where u and v are just functions from R2 to R, right? We can always write a function from C to C like this. So when we reference the u and v and the partials with respect to x and y, this is what we mean in case you've forgotten. But the functions u and v have to satisfy this very important set of identities. Partial u partial x is equal to partial v partial y. and then partial u partial y is equal to negative partial v partial x. All right. That is, the rate of change in the real part of the function with respect to the real part of the input is equal to the rate of change in the imaginary part of the function with respect to the imaginary part of the input. And then the imaginary part, or sorry, the rate of change of the real part of the function with respect to the imaginary part of the input is equal to negative the rate of change of the imaginary part of the function with respect to the real part of the input. That's a big mouthful, but that's what this is saying. It's saying that each thing changes, each component function changes, has the same rate of change with respect to its own component of the input, and then has opposite sign rate of change with respect to the opposite input component of the input. So this is the Cauchy-Riemann equations, and it is a huge constraint on what functions can be complex differentiable. So to finish out the theorem, if partial u, partial x, all these partials are defined for u and v, they exist. If they're continuous, and they satisfy these Cauchy-Riemann equations, then f is analytic on the set where they satisfy it. If f prime does exist, then, and this is where it's cool and nice, there are two different ways to write it. One way is partial u partial x plus I partial v partial x. Another way is to write partial v partial y minus I partial u partial x. And this just comes from the immediate substitutions we get right here and right here, right? And notice all this is saying is that f prime, I'll write it bigger so it's clear, f prime of z naught is equal to partial f partial x, and it's also equal to 1 over I partial f partial y. Huh. All right. It's not half bad. It's not even that weird. Fair enough. So let's delve into this. Let's actually prove it really quick. All right. So let me make sure I'm zoomed out here. All right. Okay. So let's begin with the, let's do the proof here. Make this a little teeny bit smaller, make it easier to write. Okay, so step number 1. And we're not going to prove every little piece of it. We're going to do the big part of it. We'll say suppose f prime of z naught exists. We're going to show that u and v satisfy the Cauchy-Riemann equations, the CREs, as I'll abbreviate them right here. Notice, if f prime of z naught exists, then it's given by, well, the definition of what f prime of z naught is. It's the limit as z approaches z naught of, well, f of z minus f of z naught all over z minus z naught. It's exactly the same as the definition in the regular old real variables case. The only difference, and this is why you're going to see why I stressed this so much a little bit ago. The only difference is that this chunk right here, you can approach z naught any way you want. So if this is z naught, then I could approach it, say, like this, or I could approach it like this, or I could approach it like this, or I could approach it like this, from any direction. And the limit has to be the same, or what you get, no matter what the direction of approach, you have to get the same thing no matter the direction of approach. That's what this limit existing means. Okay. So let's take the case where z goes to z naught as, we'll write it as x plus I y naught, where y naught will over here, I guess we'll say, we should maybe have started with this, but just to make sure it's not unclear, z naught is x naught plus I y naught, right? So this is basically as x goes to x naught, right? So we'll just hold the y part constant. That is, we're on a line parallel to the real axis. All right. Well, in this case, notice we'll have nothing too special. Well, it's just the same limit. Z goes to z naught. F of z minus f of z naught over z minus z naught. All right, and then I'm going to write a little bit messily right here, and instead of doing it in a nice stacked up way, I'll just go side to side. So this is just, well, it's going to be, because we're holding that y naught equal, it'll be x going to x naught of u of x y naught plus I v of x y naught minus u of x naught y naught. Oh, that comma right there is kind of overlapping with the tail of the y. Minus I v x naught y naught. All over. Well, if we go and we z minus z naught, this will just end up having an x minus an x naught, right? The y naughts will cancel each other out. All right, but wait a second. Let's break this up. If we break this up a little bit, then, and I'm doing some awful alignment in my equals here, so please do forgive me. X goes to x naught. Let's just take the pieces with i's and the pieces without i's, right? So we'll get u x y naught minus u x naught y naught, right? Over x naught, or x minus x naught. And then I'll just be adding on I v x y naught minus v x naught y naught. Oops, forgot the parenthesis right there. All over x minus x naught. All right, and hey, I can split this limit up and pull the I out front. I'll just do that really quick right here instead of rewriting everything, since it takes long enough to rewrite. Oops. Minus I lim x goes to x naught. So in here, I'm just taking, I guess I will run out. It'll get tight if I draw the parentheses, but you see I'm taking each of these limit pieces separately. But what are these two guys? The limit is x goes to x naught of, well, wait, I've got all the y naughts fixed. This is just partial u, partial x, right? Yeah, it is. This piece right here. Or did I put a minus there when it should have been a plus? I think I was writing too quick. All right, this piece right here. This is just, gosh, I should have made sure I had more room. Here, this is the best part of using digital technology, is that I can fix these mistakes relatively quickly, albeit not that cleanly. Do forgive me. It's so much easier to write on a whiteboard. I can't wait till I can write on a whiteboard again. All right. Come on now. All right. Putting the everything back right there, making it all nice and clean. This part right here, what I'm trying to say, is equal to partial u partial x, and then we go plus I. And what is this part? Well, that's partial v partial x. Hey, look at that. F prime of z naught is partial u partial x plus I partial v partial x. And if you look, that was one of the things, is partial u partial x plus I partial v partial x. And hey, wouldn't you know it, we can do the exact same trick, but instead hold the x constant instead of the y. And then, as you can imagine, just going through and doing the exact same trick, we just split up a fraction, do some canceling, write everything in terms of x and y's. Then you get the other side of the Koshi Riemann right there. And isn't that just a nice and very convenient little proof? It is such a clean result that it is kind of miraculous to me how simple it is. All we're really doing is we're just taking the direct definition of the derivative and going in and writing everything in terms of its constituent real and imaginary parts, and bada boom, it just falls right out. Basically, you can calculate the complex derivative of a function just by looking at the derivative with respect to the real part or the imaginary part. The only difference is whether or not you have to multiply by a factor of 1 over I. And if you don't recall, this 1 over I right here, if you want to remember, if we have z equal to, say, 1 over I, then notice we could multiply by a clever form of 1, which would be something like, let's just do I over I, how about? And then we would get I over I squared, and that's just minus, well, it's I over minus 1, so if you're fine with it, I would just write minus I. So another way of writing this is minus I partial f partial y, and that maybe makes it even clearer. You could just differentiate f with respect to x, or you could put the minus I derivative of f with respect to y. Kind of clean, kind of awesome. That's a very strong condition we have to have on a complex differentiable function, and is something that we should always keep in mind, something that you should definitely commit to memory. It is a very, very important concept. So let's go a little bit further now, and we'll talk a little bit about some of the nice consequences and things that come about, other things that come around with analytic functions. I have to make sure some of this did not screenshot. All right, there we go. So a little bit of that was kind of messed up, but it should be fine to go through. So before I start talking about the inverse function theorem in the complex world, another way you can go through and prove the Cauchy-Riemann equations that is illustrative and is interesting and important and does have a nice connection to the Jacobian representation that we were talking about a little bit ago, is to use a matrix representation of complex multiplication, which is a cool thing to do. And then you can go through and you can show, okay, neat, and this gives you, yeah, I mean, what they do is they basically go through and they rederive the Cauchy-Riemann equations, and they do some other nice little tricks. What we'll just proceed with the limit approach right now. It's a fine approach the other way. It's very, very useful to look at. Gives you some intuition. I encourage you to go read that part of your textbook. I believe that is pages 67 and 68-ish. They also briefly talk about what these things look like in polar. It's not too fancy or isn't important in the immediate future. We might talk about it later if it comes up, but for right now, at this very moment, they just basically go into a little bit more detail on the Cauchy-Riemann equations. Now, after that, we get to this part, the inverse function theorem. So you might remember this from real analysis or calculus. I believe we teach this in Calculus 1 at Wyoming. It is a very easy and classic result, the inverse function theorem. In regular old real variables, it says almost the exact same thing. So if you have a function from a to c, an analytic function with f prime continuous, and we assume that f prime of z naught is non-zero, then there will be a neighborhood u of z naught and a neighborhood v of f of z naught such that the induced function between u and v that f produces is a bijection. And it has an inverse that is analytic with a nice and convenient formula for its derivative. That is, it's just the multiplicative inverse of the derivative of f itself. So the idea, the picture you always want to think of is you've got, say, like z naught sitting right here. You've got f of z naught sitting somewhere else, like over here. You kind of, I guess, you got one copy of c over here. I should always put some nice little axes. And another copy of c over here. It looks like f is not really doing too much to z naught in this picture. But in either case, you got copies of c either place. What you get when f prime of z naught is non-zero is that you get a little neighborhood of some type about z naught and a different neighborhood v about f of z naught. And then the function, this induced function f, which we are abusing notation here. We really shouldn't call this function from u to v. And maybe we should make these capital U's and capital V's, because otherwise it is probably very confusing given what we've been using for the real and imaginary parts of a function. These capital U's and V's. This f, really, it's not exactly the same f, right? This f really right here, since f goes from a to c, we could take f restricted, say, to u, and that would go from u to c, and then we could form some fancy map, let's call it f tilde, that goes from u to v, such that, say, f tilde iota composed with f tilde is f restricted to v, or to u. Sorry, that's a u, not a v. Where iota is the inclusion map that sends v into c just by taking this subset and embedding it in the bigger one, right? So this is, if we wanted to state everything very accurately, what we're really saying is that this f tilde map has it is a bijection and has a nice derivative. But no one likes to state it like this for, I think, at least maybe I'm being overly judgmental. I think a kind of obvious reason, which is that that's sort of ugly to look at. But be very careful. This is a local property. That's what I'm really trying to drive home. This is a local property. This is not something that you can say about f just all over the dang place, right? It's something that you can say about f in some neighborhood of a point and some neighborhood of the image of that point. And you get this nice formula where you say, hey, the derivative of this inverse function is given by 1 over the derivative of the function. And that's a nice little thing. You have the same sort of thing in real variables. The only interesting difference here is holomorphy. Basically, nothing fancy is happening, just because, think about, you've got, all these holomorphic functions are also, or analytic functions are all also real differentiable as well. They just have to satisfy some kind of restrictive conditions. So, of course, things from real variables carry over just like this, and we get nice inverse function theorems. So I won't go through and reprove the inverse function theorem. It's not necessary. You can go look it up in any calculus textbook. We can also just notice that, and this is what I was saying, this is the real variable inverse function theorem. So if you recall a function from a subset of R2 to R2, if you have it continuously differentiable and the Jacobian, the matrix of partial derivatives, has a non-zero determinant, then there are neighborhoods U of 0, 0 and V of U of x naught, y naught, and V of f of x naught, y naught, such that this induced map between U and V is a bijection, and the derivative is of the inverse function. The matrix of partial derivatives of the inverse function is the matrix inverse of the matrix of partial derivatives of the function. So once again, the multiplicative with respect to matrices, inverse. It basically says that the derivative of a functional inverse is the multiplicative inverse of the derivative. It's kind of a nice trick. Same thing. Just all we have to remember here is that for a if we're looking at something, writing f in terms of u's and v's, this is partial u, partial x, partial v, partial x, partial u, partial y, partial v, partial y. Let me make sure. Did I say that? Did I do that right? Do I do it? Yeah, okay, perfect. Oh, no, I should have written it. Sorry. Partial. What a fool I am. Oh, my gosh. Sorry. Writing too quick right here. There is some question of which way you should write. Do you go u's across and x's down, or do you go u's down and x's across? Ultimately, it's the same as taking a transpose. If we're talking about ranks or things like that, determinant shouldn't change too much, but we'll just keep it very consistent. My apologies for the small mistake right there. All you have to do is just notice, using the Koshi Riemann equations, this becomes partial u, partial x, minus partial v, partial x, partial v, partial x, and partial u, partial x. So that is, we're going to do everything in terms of x's for a moment. And notice that when I take the determinant, I just get partial u, partial x squared plus partial v, partial x squared. And hey, wouldn't you know it, this is just the modulus, by, once again, the Cauchy-Riemann equations of f prime of z. Squared, of course. Modulus squared, because otherwise we'd have a big square root right there. So, kind of a neat little piece, right? Just to notice that that the determinant there measures the squared modulus. Kind of cool. So you can go through and you can determine the inverse of the matrix using all sorts of nice little things. They do it in some painstaking detail, which takes about 2 pages in the textbook. We won't go further than that. It just is nice to see this little fact right here. You can go through and you can show everything out. There's nothing fancy or exceptional. Basically, just the thing to notice is that when you do the Cauchy-Riemann equations, apply them, you can turn this real variable inverse function theorem into the fancy complex inverse function theorem. So there's nothing weird going on there other than we're just taking a result from real analysis and then we're applying some of the constraints that are imposed on holomorphic functions, and we're seeing what happens. After that, sorry, let me insert another layer right here so I have a bit more room to write. After that, the next thing that we need to talk about, and just to kind of circle back to what we've learned so far, last time around in part 1, we basically talked about what complex differentiability meant, how it looks almost the exact same in terms of the definition, but there's an important difference in terms of what the limit as z goes to z naught means. Then we said, hey, pretty much everything we know from the regular old calculus world carries over. We have chain rule, we have additivity, we can pull out scalar multiples, linearity of the derivative, all this nice stuff. And then we found out about the Cauchy-Riemann equations, these very important facts about how the rates of change of the real and imaginary parts of a holomorphic function have to behave with respect to the real and imaginary parts of the input to that function. And then we, talked about that a little bit. We found out that yet more things that we're familiar with continue to hold. We used the Cauchy-Riemann equations to get there. We didn't show how we use them more than just kind of hinting at this little determinant trick. Go in your textbook and read that part if you want to see the rest of the gory details right there. It's nothing too fancy, but it is satisfying. And so basically the entire moral of the story so far has been, hey, you can do calculus with complex valued functions. You can get lots of familiar things, pretty much everything, all of the familiar results. You also get this extra interesting constraint called the Cauchy-Riemann equations, this nice fact. And now we're going to start asking about some of the consequences of the Cauchy-Riemann equations. Namely, so the real and imaginary parts of any analytic function, any holomorphic function, must satisfy the Cauchy-Riemann equations. So that is, if you have f, and we'll write it again as x plus iy. I'll write it like this. This is u of x, y plus v of x, y, I, or iv of xy, doesn't matter which order you write the multiplication. These u's and v's have to satisfy some nice properties. There's an important thing that you might encounter outside of this class called a harmonic function. A function, let's just call it u for now, from let's just even write it as from R2 to R. We don't need it to be all of R2, but we'll just write it like that for the moment. A function u from R2 to R is harmonic if partial squared u partial x squared plus partial squared u partial y squared equals 0. Another way to write this that you might have seen would be to write this upside down triangle squared u. This is called the Laplacian. So a harmonic function, that is, u is harmonic if it has we could say 0 Laplacian, a Laplacian of 0. So this is supposing, of course, that U is twice continuously differentiable. To write something like this, maybe I should say that a twice continuously differentiable function. It is occasionally abused outside of that. But this is generally what people are referring to when they say harmonic. It is something where the second partials add up to second pure partials, right? Not partial squared u, partial x, partial y, right? The mixed partials. The pure partials, they add to 0. Now, an important fact about now this is another place where your book sort of spoils the fun, and so I'm always loath to say it because it is satisfying to find out yourself. A big and amazing thing we will learn in chapter 3 is that all analytic functions, all holomorphic complex differentiable functions are infinitely differentiable, which is crazy. This is actually like an insanely huge deal and will be it'll drive a lot of what goes on, and it amazingly just is a consequence of things like the Koshi Riemann equations, which of course itself is just a consequence of how we describe or define the derivative in the complex plane and having more than one direction of approach. So this once continuously differentiable implies infinitely continuously differentiable result, which we won't prove now. We'll do that in chapter 3. This is a real big deal. This will tell us essentially that the real and imaginary parts of a holomorphic or analytic function are harmonic. And this is a nice fact. I will put it up now. If f is analytic on an open set A, and f is given by u plus iv, that is u and v are the real and imaginary parts of the function, then both u and v are harmonic on A. All right, so this has a nice and pretty little proof. I actually just put the whole thing up here because it's so dang short, and it just uses the Koshi Riemann equations. It shows how these seemingly obvious little facts, so simple, just, approach with the real part fixed or approach with the complex part fixed, and you get these two different equations, and hey, they have to be equal to the same thing for the thing to be differentiable. These two very simple equations, this really shows just how much you get out of there. So there is a big caveat. We are assuming u and v are C2. That is 2 times continuously differentiable. They are, but we haven't proved that. They are. We haven't shown it yet. I just want to say that because it's important to always be clear about your assumptions, and we shouldn't be lying here. So, anyways, if we can accept that for a moment, that we will prove it later on in chapter 3, let's use the Cauchy-Riemann equations. That is, the partial of u with respect to x is equal to partial of v with respect to y, and the partial of v with respect to y is equal to the negative of partial of v with respect to x. If we go through and we just differentiate partial u partial x equals partial v partial y with respect to x, and then we do the second one with respect to y, well, we'll just, add it over there. So this is just, we're going partial x of partial u partial x. That's equal to that, obviously. This chunk right here is just partial x of partial v partial y. So just this first equation, if you're not seeing it. We do the same thing to the second one. This guy, which annoyingly is split across 2 lines. I hate it when people don't format their text to avoid that. There's a single command you can type in LaTeX to make sure that doesn't happen, but some people don't care. Anyways, you just do it with respect to x on the x part, respect to y on the y part. And then by the symmetry of second partials, another result we won't prove, but a classic thing from, I think you probably have seen this in Calc 2, that the second partials are symmetric for continuous functions. So partial v, partial x, partial y is equal to partial squared v, partial y, partial x, this fact. Since we know this, we can add the two together, and this chunk right here, because we've got that negative sign thanks to the Cauchy-Riemann equations, they cancel each other out, and so adding this piece and this piece is the same, obviously, as adding this piece and this piece, which are 0, right? And so, hey, wouldn't you know it, partial squared u, partial x squared, plus partial squared u, partial y squared is equal to the other side, and that's 0. And you do the exact same thing for v. Pretty dang cool, pretty dang smooth. We've just immediately gotten a nice fact about the real and imaginary parts of any holomorphic function just right out of the Cauchy-Riemann equations. Kind of cool. So this turns out to be a very big old deal, and it's kind of nice. So one of the things, I should before I go on there, I should make sure I don't spoil the fun. One of the things you might ask, looking at this result, okay, so, and this is always a good kind of thing to ask in mathematics. We've got a result that says, hey, if you have an analytic function on an open set A, and you have then the real and imaginary parts are harmonic. Okay, cool. Now, what if I have some harmonic functions on a region A, an open set A in complex plane, or an R2? Are they the real and imaginary part of a analytic function? That is, the question here becomes, is every analytic function just a pair of harmonic functions? Or is it the case that you have harmonicity for the real and imaginary parts of an analytic function, but having harmonicity is not by itself enough to get analyticity? And so it's just asking the opposite question. So analytic implies each chunk is harmonic, but is having 2 harmonic chunks enough to build you something that's analytic? And the answer to this is given by proposition 1.5.13. If you let u and v be harmonic conjugates on a region A, that is, and I should define what this means. Let me stay back here for a moment. I will tell you the next piece a little bit better. But the answer to this is I think I have to use this chunk here first if I want to. I forgot about this piece. I almost spoiled the fun. But I'll just spoil it a little bit ahead of time, and I'll tell you what the answer is. The full answer is ultimately tricky, but if you think of it like this, derivatives are a local concept, right? If you want to take a derivative, then you're just you're differentiating at a point. It's a instantaneous rate of change, right? It's at a point. And you can have derivatives at multiple points, and you can have these derivatives very continuously or something like that, but it is a local property. Since being harmonic is defined in terms of a derivative, it as well is a local property. And so the answer to the question of whether or not having a pair of harmonic functions is enough to give you a pair of harmonic functions, say like satisfying the Koshi Riemann equations, or just a pair of harmonic functions. Can you get, I think I've put this out of order right here, and I apologize for that. Can you get, yep, there we go. That's the issue. That's what happened. Can you get a, all right, can you get an analytic function? Well, here's an easy kind of piece to that. The ultimate answer is kind of hard, but basically the idea is that if you have a twice continuously differentiable harmonic function on some open set A and a z naught in A, then there is some neighborhood of that point on which u is the real part of an analytic function. All right, you can naturally imagine that the same probably works in the opposite direction, right? Or not in the opposite direction, but with the imaginary part of the function as well. This ends up being a more interesting and difficult thing to prove in general about when things are, when harmonic conjugate pairs give you analytic functions, and we will talk about this more. It turns out to be the case that you need things like infinite differentiability and a lot of things I don't want to necessarily spoil later on. And one of the interesting pieces that will happen, so here, let's go back to this piece, which is what we were, if I had remembered right, this is what we would have built to. If we have harmonic conjugates, which means that f is u plus iv for some holomorphic or analytic, as we're saying, analytic f, right? Harmonic conjugates, right? If u and v are harmonic conjugates on a region A, and the equations u of xy is equal to some constant and v of xy is equal to some constant, these guys, of course, define smooth curves, right? If we'll suppose that they do at least, right? Then these curves intersect orthogonally. So let me show you what we mean. And this is kind of similar to some of the pictures we drew previously with the conformal mapping theorem. If u is constant and v is constant, you should be getting, for example, here's the some harmonic conjugates. U is x squared minus y squared, and v is 2xy. That is, f of z is z squared, right? You actually just, write z in terms of x's and y's. We've done this in our homework. The real part is given by, actually, since we've done this in our homework, this is actually one of the pictures from the homework. I've just superimposed it, right? This is the parabolas, right? That we were graphing, the parabolas, remember? That lines parallel to axes go to parabolas. These are the hyperbolas, right? Oh, or at least part of the hyperbola. We'd have other chunks down here, right? Anyways, these guys that we've seen in your homeworks are what we were drawing. What we have to have, as it turns out, is, and this is cool, that the intersections of these pieces, and if you kind of draw your tangent lines, it is not terribly hard to see. These guys have to be at right angles, right? They intersect at right angles, which is absolutely nuts if you think about it. It is kind of cool. It is sort of ridiculously difficult to come up with things like this if you're just drawing and not using mathematics. If you just try to go like, how can I make everything intersect nicely and stuff? It feels hard. It feels hard to draw nice pictures where this happens. But awesomely, and maybe expectedly because of the the conformal mapping theorem. Harmonic conjugates, the real and imaginary parts, satisfy these. Looking at their level sets, the values of x and y that equal a given constant, their level sets intersect orthogonally at right angles, and this is in some ways just a consequence of the conformal mapping property of a holomorphic function. And I feel like the end of this has become slightly disjointed. I apologize. We were just running up at the end of time. This is the last theorem of the section, last proposition. And don't worry about this piece, this part that we've. I think I really kind of. I'll be honest. I botched describing what the answer to this piece is. I hope it wasn't too confusing right there. If it felt confusing, just ignore it entirely. We'll come back to this question later about when harmonic or pairs of harmonic functions describe analytic functions. But for now, it's just food for thought. You don't need it on the homework. The homework that's due Friday, we have everything we need so far. And it is not too bad at all, since basically most of this chapter, other than the Koshi Riemann equations, is a fancy way of saying, yeah, you can do all the usual stuff from calculus. So if anyone has any questions, throw them in the chat now. Or, type like yes if you have a question, so I don't have to wait around to see if anyone is going to ask one. And yeah, we'll end it for tonight. I'll answer questions if people have them. If not, we'll pick it up on Friday. And remember that your homework is due on Sunday. I think I might have just said a second ago that it was due on Friday, in which case I apologize. It is due on Sunday, but that you have everything you need for it now, and it is not too bad. Basically, just do calculus, but with a little bit of extra care. All right, I'm not seeing any questions in the chat, so without further ado, have a great night, and I will see you on Friday. Bye.